Hey everybody. Um so this is Wednesday's lesson and I wanted to just do another example of solving a network. Last time's lesson was kind of long. I want to keep these shorter than our normal class time because you can't talk to me or ask me questions, so we can cover more information. And so I just want to do another network example to kind of get you more into these minimum cost flow networks, okay? And then I'll send you a homework problem of one of these sometime this week. All right. So here's our example. It's the network here. It's just 4 nodes and I got 5 arcs, so not too complex. The things in red are the cost of taking each unit on each arc here. And the blue are the supply and the demands. So this one has 3, this one has 2, and they need to ship so that this one has 2 and this one has 3. Okay? And so this is a balanced network because you do have a total supply of 5 and a total demand of 5. We're not going to get into unbalanced networks in this class, but it's actually not that hard to solve those. It's actually pretty easy, but I don't want to give you too much craziness to think about. All right? So for right now, just like with LPs, we don't know how to get a starting solution yet, or just like we did with LPs. So I'm going to give you a starting solution, okay? And what we would like to do with our starting solution is assign dual values to each node. So I give you the first one. Remember, we're going to put a root. Literally, you could put the root on any of these if you wanted to, but I always just started at the first node. And we'll just say that dual is 0. And so then we want to work our way around finding all the dual values. Okay, remember how we get the duals though. It's the original cost minus the dual tail plus the dual head. So what's the original cost on 1, 3? The original cost was 1. I already have the original cost in for us. What's the minus the dual tail, which is 0, plus the dual head? We don't know what this is, but we want it to equal 0. So that means that this dual cost is going to have to be negative 1. 1 minus 1 equals 0. So let me write that dual in there. Negative 1. I'll keep those duals in red. Alright, so now we need to figure out the dual on 4. Well, what was the original cost on 3, 4? It was 6. I wrote a 2 for some reason, so let me scribble that out. It's a typo in the problem here. So 6. So minus the tail. Oh, I know the tail now. It's negative 1. Plus the head. Okay. Well, what's the head going to be? Let's see. Well, 6 minus negative 1. That's like 6 plus 1, 7. Plus something has got to equal 0. So this has got to be negative 7. So the dual here is negative 7. Okay, now we got to find the dual on 2. So what's the cost of 2, 4? It is 2. Cost of 2, 4 is 2. Minus the tail. I don't know the tail. Plus the head. I do know the head this time. That's negative 7. So what am I going to need right here? I'm going to need a negative 5. So this dual is negative 5. Okay? So are there any questions on finding the duals? So I gave you this starting flow. Let's check to see if it's a feasible flow. 1 has a supply of 3, and it sends all 3 of them down to node 3. Well, 3 had a demand of 2, so it took 2, and it had an extra, so it sends it on to 4. 2 had a supply of 2, so it sends its 2. And 4 had a demand of 3, and it's getting 2 plus 1 is getting 3. So that is primal feasible because all the supplies and demands are being met or shipped away. Okay, so we found the duals, and we found the duals with this original cost minus the dual tail plus the head. It's got to equal 0. Okay, so now what we want to do is we'd like to check these 2 arcs that are not in the basis to see which of these 2 arcs, this one or this one, we want to see which of these 2 is most attractive to enter the basis. Just like we would with our LPs, we do check the reduced cost on these 2. Well, how do we get the reduced cost? It's actually the same formula, the original cost minus the dual tail plus the dual head. That's why we had to get the dual values to start the problem. Now we have the dual values. Now I can find the reduced cost. Okay, so x 1, 2, that's this one right here. The original cost is 3. I've put that 3 in there for us. Minus the dual tail is 0. plus the dual head is -5. So let's see, what do we get? We get a -2. So that is an attractive variable there, okay? Let's see which one is more attractive, though, because negative reduced cost is more attractive. We're trying to minimize the cost. So 2. So let's see. 3, 2. What was the original cost? 2. I have that in there for you. Minus the tail. What's the dual on the tail? -1. Plus the dual head, which is -5. So let's see, that's 3 minus 5. That's also -2. So they are both just as attractive. Okay? So when there's a tie, you can choose either. I'm going to choose the one that's smaller lexicographically. Remember what that means is it has a smaller index. So I'm going to let this one be the one to enter. So what we do is, the way we show this is we go over on our network, and typically people draw a dotted line for the one, the variable or the arc that they are entering. So x12 is going to enter, just like we did with the normal LP solving. We had a variable entering. Now what's going to leave? Let's figure out which arc is going to leave. Okay, so what we're going to do is, notice this is entering in right here. Let's find the cycle that it creates. It creates this cycle right here. So let's look at any that push back the wrong direction. This arc 3, 4 and the arc 1, 2 push back in the wrong direction. So we're going to push some of the flow this way. Which one would be pushed down to 0 first? Okay, so if I push 1 unit, that's going to add 3 here. It's going to take 1 away from here. That would be 0. Take 1 away from here. That would be 2, right? So this one is a smaller flow. So the smaller flow in the wrong direction is going to be the one that's going to be taken out. So this one's going to leave. Okay? So we have 1, 2 entering and 3, 4 leaving. Does everybody understand how you find the leaving variable and the entering variable? Okay? And it would have been fun to do this example twice to see what happens when we choose. This is the entering one. That would, let's see, just with my mouse here, that would be right here, and the cycle would be created right here, and it would still kick out the same one. It would kick out this one. That's the only one in that cycle moving in the wrong direction. So that would be comparable cost. Actually, it would be the same cost, because if you send that unit here, it's 3. If you send it here, then here, that's also 3. But ignore what I said if you got lost in that. All right, so now let's make the pivot. So to make the pivot, we want to redraw the network. Okay. See if I can draw it as neatly as I had it. Redraw the network. Get our root node number 1, 2, 3, and 4. And let's put the arcs in there. So we're going to have this arc entering, this arc staying in the basis, this arc staying in the basis, and 3, 4 left the basis. It is a connected, rooted spanning tree. That's good. Okay, let's figure out the flows. Now here's how we can figure out the flows. Go back to this cycle we looked at. This was pushing 3 this way. We're going to push 1 unit, and you can go 1 at a time until you push this down to 0. So I can push 1 unit here. That's going to give 2 an extra one to send. So 3 units will flow there. 1 less unit here would make that 0, and this would only have 2. So you go along the whole cycle and you adjust the flows depending on what you're pushing here. So I am now pushing 1. Let me do that in blue. I already got blue. 1 there. This is going to be 3, and this is going to be 2. So we do need to make sure the demand and supplies are met. If you look back up at the top, I'm not going to scroll so that you don't have to look all over the place. This had a supply of 3. It is sending out 3. This node right here had a demand of 2. It is getting its demand. 2 had a supply of 2. It's getting 1 sent to it. With its 2, it is sending 3 to 4. And 4 had a demand of 3. So everything is primal feasible. That's great. So we need to find the duals. So remember, we're going to let this be 0. And so let's see. 1, 2. So the original cost, which is 3. If you look back up, the original cost on that's 3, minus the dual head, which is 0, plus the dual tail. To make it equal 0, that would need to be a -3, right? So the dual here is -3. Let's do x1, 3, this arc. The original cost was 1 minus 0. This is going to need to be plus -1. So that dual value actually didn't change. It was already -1. And then finally we get to the dual of 4. The original cost here was 2 minus -3 minus the tail plus the head. What's that going to need to be? Well, let's see here. 2 minus -3, so that's 2 plus 3 is 5. This will need to be -5. I actually could have already guessed that was going to be -5. I'll show you why. So we cut this one, and the only duals that are going to change are the where we added the arc and any that are flowing from that, not connected back to the root. So we cut it here and then add it on here. So anything from here is going to change. It's going to change by the same amount along this whole. So if I had more nodes, say this connected to 5 and to 6, all of these duals would change by whatever this one changed by. How much did this change by? It increased by 2, from -5 to -3. So I knew this one was going to increase by 2, from -7 to -5, and all these would increase by 2 that if they were connected into it. Okay, that's just a trick. You don't have to know that. It should make sense because the original cost are always going to be the same, but what you're subtracting off these subtractions or these tails and head values are going to change. Okay, so there we sit. That's awesome. We've done the pivot. Now we need to see if we have anything attractive. So let's find the reduced cost. Okay, so the only two possible ones to enter are 3.2 and 3.4. So we need to check the reduced cost on these two. Okay, so the original cost on 3.2 is 2 minus the dual tail, so minus -1, plus the dual head, so -3, and we get 0. 2 plus 1 is 3, minus 3 is 0. That's interesting. I'll talk about that in a second, okay? Now let's do 3.4. The original cost was 6 minus the dual head plus the dual tail. And so this ends up being positive, so definitely not attractive. Not attractive. Okay, so notice we have no attractive cost, so nothing's attractive. Nothing attractive. So we're optimal. So this is our optimal table right here. Let me erase the dotted lines so they're not table. What is this thing called? Optimal network. So let's see if we can do things like find we see the flows. We're sending 1 here, 3 here, and 2 there. Let's see if we can find the objective function value, which is really not that difficult to do. All we have to do is take the cost times its flow. So let's see, what was the cost on 1.2? Cost on 1.2 was 3 times its flow, which is 1. The cost on 2.4, cost on 2.4 was 2, and its flow is what, 3. And then finally, what was the cost on 1.3? The original cost, if you look back, was 1, and we were flowing 2. So let's see, what is this going to be? That will be 3 plus 6 plus 2, so 11, if I'm adding correctly. So we get an objective function value of 11, whatever units we're in. All right, now I do want to talk to you about one thing. Notice we get a reduced cost of a 0. That's not attractive, it's not negative, but it's also not positive. So that means it would have 0 effect on the objective function value. This is just like doing LPs. This means that I have alternate optimals. So I could pivot this in and look at it, but we're not going to do that with these networks at right now. We're not going to dive too deep into this. This is just a fun extra topic I'm throwing in because it's really cool and it's covered in all intro LP classes. But you don't have to go that deep. But could anybody guess this was coming? You kind of should have seen it up here because we had two things that were equally attractive. Now that doesn't always mean I have alternate optimals, but since this is only a one pivot problem, that thing at the one pivot could have gone either way, and then I was optimal. You should have probably guessed that it would have been the same z of 11 actually. So this actually does have an alternate optimal if you were to cycle in 3, 2. If you did cycle in 3, 2, notice the cycle it makes is right here. It would push out 1, 2, which was the one that was even with it, and you would have this flow right here, like a Z almost. Okay. All right. Now I do want to mention something. I'm not going to show this to you because it goes deeper than I want to go in an intro LP class. But I do want to let you know that I've given you the starting solutions. But does anybody have any guess how you get a starting network? Any guesses? Well, it should come as no surprise to you that there actually is a two-phase network simplex. And you should Google it for kind of, you might can just, Google it, but some of the things you're going to see are probably going to be weird if you Google this, but there is a two-phase. Some of y'all are going to love this. To do the two-phase one, what you do is you add an artificial node. So say on that network we just had, network looked like this. You add an artificial node, and all of these things you're going to draw, some of them will be two of it, some of them will be way, depending on if they have demand or supply. I think these had demand and these have supply. You put the root here actually, and you would do pivots until none of them, until we're done being connected to the artificial, besides just one of these, which will become the root. So it's pretty interesting. The cost on these are positive ones and negative ones, just like we would put the cost on our artificials in our tables as -1 or +1, depending on if we're minimizing or maximizing. So that's pretty neat. I don't want you to have to do that though. So if I do put this on the final, I will give you a starting simplex network, and you will just do a pivot or two, okay? All right, awesome. I'm going to let you go. You'll have a wonderful night. I will talk to you later.